All right, today we're going to go over 7.3, which has to do with proofs using multiple assumptions. Note that I know we did not go over exam 3 in class. However, I have released the answers on Scholar. So if there are sections of that you want to review as part of your final exam prep, you can now do that. If there is a specific question that you want to discuss on exam 3, probably the best thing to do is to mention it during our in-class review next Wednesday. But if you want a quick answer, you can also email me. On Monday, we will do 7.4. On next Wednesday, as I've said, is our in-class review. Our final exam, I already announced the time of our final exam, but now I've left my sheet with it at home. Did I say, is it 11 o'clock on Friday? Does that sound right? Oh, okay, it's the late one. It's Wednesday of exam week, so it's towards the end. Okay, very good. Well, I'll announce that again next week, and I'll triple check the time. Let's see, is there anything else logistical I should mention? Again, there's a tutor-led review next week. I believe that is Tuesday night online. Any logistical questions? All right, well, let's talk about 7.3 and how to do complex proofs requiring multiple assumptions. So here, sometimes there are inferences, sometimes there are valid arguments, but you can't prove that the conclusion you're supposed to prove follows just using the rules that we've taught you so far. So here's an example of one. If A, then both F and P. If not A, then both S and R. Not R, those are our three starting given premises. From that, we want to prove P. So we start with our first step. So what is the first step in any problem covered in chapter 7? We assume the opposite of the intended conclusion. So we can assume not P, but then we look at that and we can't do anything because you need like a not F and P to do modus tollens on statements 1, and you need a not both S and R to do modus tollens on statement 2. And an A or not A would be really useful, but we don't have anything like that. So what do we do when we're stuck like this? Well, let's take a look at what the truth assignment test would do. And this is why sometimes truth tables are more powerful than truth assignment tests. Because if we looked at the truth assignments, if we try to force the argument to be invalid, we could get the value of R as false because we want premise 3 to be true. We could get the value of P to be false because we want the conclusion to be false. But then we're left with 3 variables, 3 statements that we don't have values for. And when we plug in the false for R and P, it doesn't get us very far. We still don't know whether or not these whether or not this is set forth an invalid set of values here. So we haven't made much progress. So what can we do back? Try and use S and I rules on this more complex argument. And the answer is we can make an additional assumption. So here is the hardest principle to understand. So listen close. You are allowed to make absolutely any assumption when doing a proof. So long as you block it off from the rest of the argument and keep it into a separate sub-argument where your goal is to get a direct contradiction. So just like starting off every argument by assuming the opposite of the conclusion to get a contradiction to prove that the conclusion is in fact the case, you are allowed to make an additional assumption, any additional assumption, in a separate sub-argument, try to get a direct contradiction, and then you confer out the opposite of your second assumption. Let me talk you through what this looks like. So we've got our problem here. We've got three given premises. If A, then both F and P. If not A, then both S and R. Not R. We're trying to prove P. We start with not P. But not P doesn't let us do anything. So then we should make an assumption. And note, I've indented the second assumption in farther to indicate that it is a second nested, it's farther nested in. You can't use that assumption on its own long term. You can only use it as part of its own separate subproof. But I've assumed not A. And why did I assume not A? Well, again, I could have assumed anything I want. But I'm going to assume not A, because that's going to let me do an inference with 2. And eventually, I will derive from the subproof the opposite of my new assumption. I will derive an A. That's where I'm going to get after I get a contradiction from assuming not A. And the proof ultimately will start to look like this. Step 6, we will take the not A, plug it into premise 2, which says if not A, then both S and R. So I'll get S and R. Then step 7 and 8 will be to grab both halves of step 6. We'll get an S and we'll get an R, because when you've got an and, you can get both halves. And the minute we get to step 8, which is R, what do we have? Well, we have a contradiction. We have statement 3 says not R, and statement 8 says R. And once you've got a contradiction, you get to derive the opposite of the most recent assumption. So then you get something that looks like this. So you see what we just did was this subproof, and I've indented it extra far in because it is separate from the rest of the argument. The only thing that these premises are good through, the only thing that 5 through 8 are good for, are for getting to the contradiction in 8 and showing that not A can't be the case, so that in step 9, we can infer the opposite of not A, which is A. Now, once we get to 9, we can then never go back to 5, 6, 7, or 8. Those are now out of bounds. And the reason they're out of bounds is we've shown that those are part of a separate subgroup. The only point of 5, 6, 7, and 8 was to show that 5 can't be the case, so that we could get 9, which is the opposite of 5. So literally, if you like covered over 5 through 8, that might, if you're tempted to use 5 through 8, then like put a piece of paper, because you're not allowed to use them. All right, now at this point, we can go back to 1, 2, 3, 4, and 9. And we want to ask, are there any inferences we can do with 1, 2, 3, 4, and 9? And the answer is yes. Now that we've got 9, we can go to statement 1 and plug 9 into 1. 1 says if A, then both F and P. 9 says A. You plug that in, and you get step 10, which is F and P. Once you've got F and P, which is an and statement, you can get steps 11 and 12 where you take both halves of the and out. So you can get an F and you can get a P. And once you reach step 12, you have another contradiction. You have a contradiction between P in step 12 and your initial assumption, not P. And once you have P in step 12 and not P in step 4, you have a contradiction which allows you to get the opposite of the initial assumption in step 4. That allows you to get your final to be proven statement P, which was to be proven. Bam, you're done. Now, here's a fun thing. There was more than one right way to do this problem. So I've shown you only one correct way. But there's another thing you could have done. So look back at this step here. Let's say for our second assumption, we wanted to do something different. Instead of not A, we might have just assumed A. And if we'd assumed A, instead of doing steps 5, 6, and 7 from not A, instead, if we'd assumed A, we would have done these steps, 9, 10, 11, and 12. Those steps would have been our 5, 6, and 7, and 8. And at that point, we would have derived the opposite of our A. We would have derived not A. So if we'd assumed A rather than not A, basically 5 through 8 and 9 through 12 would be flipped. And you would have still done all those inferences, but you would have done them in a completely different order. You still would have gotten to the same place. If you didn't understand everything I just said, here's what you should know. There was more than one right way to do this. And there was a way to do this by assuming A rather than not A in step 5. And you just would have done the inferences in a different order. So this gets back to what I've been saying. We're becoming philosophical grown-ups. There's more than one right way to do these. There's still a hell of a lot of wrong ways to do these, but there are, in fact, more than one right way to do these. And that's just like life. Okay. Pause for thoughts, questions. I have just given you your weapons.
When you're doing the, I guess the concentration of both, would it be better to do like what you would the algorithm to assume a letter that's already in the first like 3 years old?
Yeah, so usually what you want to do is the second assumption, you want to assume something that's going to let you do an inference with something that's up there. And if you can actually think a couple steps ahead before you choose the assumption, you want something that's going to let you do some inferences and eventually get to a contradiction. So that's the gold standard, something that will let you do more inferences and ultimately get to a contradiction. And if you're not sure, this is where trial and error can come in. I mean, you're allowed to, try plugging something in, see that it doesn't go anywhere, and then take out that eraser. Yes?
When you do the break, in the second function, do you change the letter? Like, if it's like immediately not?
Well, what you do is what we did in step 9. Once you're done with 5 through 8, you get the opposite of whatever you assumed in 5. So that's the change you're allowed to make. But then other than that, you're not allowed to touch 5 through 8 again. Is that what you were talking about?
So like, say for like number 5, you said it's not A.
Yes.
And so that you do, but so could you also say assume A but still?
Well, you would have assumed A, and that would have been actually to go with 1 rather than 2. But if you'd done that, then step 6 would have been, you would have plugged A into if A, then F and P, and you would have derived out F and P from your step 6. So you see what you would have done differently? Yeah. So either of those is correct. Either of those is 100% correct and legitimate way to proceed. Which is kind of what I was trying to say when I said there's more than one right way to do this. In fact, I mean, you probably could have done some really weird stuff. You probably could have assumed like not both S and R in step 5. And yeah, there were probably some other things you could have done. But when in doubt, keep it simple. Because, you know, a 13-step logic proof with 2 assumptions. That's our idea of simple here in the next to last week of class. All right, well, let me go over some principles here. Because if you're feeling a little stunned or shell-shocked or what the hell am I supposed to do, let's give you some rails to run on here, because I've just given you the logical equivalent of nuclear weapons. And you need to be careful what you do with it. How do you know to make more assumptions? Well, first, you make more assumptions when you are stuck. That means that if there's more S or I rules that you can do, you don't just go making assumptions because you can. I mean, this is, you know, sort of your tool of last resort. You want to use your regular S and I rules first. You want to do all the possible inferences first. Because if you start assuming things when you don't have to, I mean, there still might be a path to getting the problem right, but at the very least, you're going to make the way to the end longer. So you don't want to use this, you know, this is a tool of last resort. You don't want to use this unless you really need to. And then here is, so that's one question. When do you make extra assumptions? Only after you've done everything else that you possibly can using the S and I rules and you haven't gotten to the end of the proof. But here is really the magic question. The magic question, most people can figure out when you're supposed to make an assumption. The $64,000 question is, what should you assume when it's time to make the extra assumption? And the golden principle is the first bullet point. Assume something that allows you to use an inference with an already existing complex, well-formed formula. So look at what you've got in your arguments. Look at the complex statements that use I rules. So you want to look at arrow statements, you want to look at or statements, and you want to look at negated and statements. And you want to assume something that lets you do an inference with one of those 3 kinds of statements. So you either want to assume the left side of an arrow statement or the opposite of the right side of an arrow statement. You want to assume the negation, the opposite of one of the 2 sides of an or statement. Or you want to assume the match of one of the 2 sides of a negated and statement. Yes, sir.
Wouldn't you want to assume not A, that when you contradict it,
No, and here's why. If you assume not A, the purpose of the assumption is to let you do an immediate inference. So you're right, at the end of the day, you're going to want the opposite of that to be something that you can use somewhere, but your most immediate need is to do an inference now. So if you can go farther ahead, you're asking questions that draw into considerations farther ranging issues. Really, the ideal thing to assume is something that will let you do an inference now, and will let you get some sort of inference later with the opposite. So that's kind of the ideal thing to assume. But most people, a lot of people at this point aren't able to look that far ahead. So you're not wrong that that's a concern, but that's a little more advanced than what a lot of us are worried about right now. All right, how many of you would like me to do another one? I should do another one, right? Yeah, let's do another one. Okay, so statements 1 and 2 are given, and we're going to try to prove. So statement 1 is if A, then both B and C. Statement 2 is if B, then both A and C. From that, we're going to try to prove if either A or B, then C. Okay, so step 1 is easy. Assume the opposite of the intended conclusion. So we're going to assume it is not the case of if either A or B, then C. Then we look at 1, can't do any rules with 1, can't do anything with 2. But number 3 enables us to use an S rule, negated conditional, if, negated if then. So from statement 3, we get the match of the left side of the arrow statement. We get either A or B, and we also get the opposite of the right side of the arrow statement. We get our not C. But then we look at 1, 2, and 4, and we still can't do any inferences. But we've also not yet gotten to a contradiction. So what should we do? Well, the correct answer in statement in section 67.3, if we are stuck in attempting a proof and we haven't gotten a contradiction, that is when we make our additional assumptions. So let's look at this and just think through some of the things that we might consider assuming. We might consider assuming A, because if we assume A, then we'll get B and C out. We might consider assuming B, because if we assume B, we can get A and C out. We might consider assuming not A or not B, so that we can do an inference with 4. So again, this is one of those situations, there are multiple right ways to proceed, and there's probably at least 4 fairly straightforward ways we could proceed and be absolutely correct and do well. All right, so let's assume as our second nested assumption, let's assume not A. Well, not A is going to let us use the or rule with statement 4. Statement 4 says either A or B. Statement 6 says A, so that will get us B. Either A is true or B is true, but A is false, so B must be true. Once we've got B, in step 7, we can use premise 2 with it. If B, then you can get both A and C. So we've got B in 7, we've got if B, then A and C in 2, and we infer out both A and C in 7. Once we do that, we can use the AND rule and take A out of line 8. And once we take the A out of line 8, we then have a contradiction. We have not A in step 6. We have A in step 8. Those are the opposite of each other. And that enables us to get the opposite of our nested second assumption. We get the opposite of not A, which gets us A. So then in step 10, we get our A because lines 6 and 9 contradicted. We then block off and ignore steps 6 through 9 because that subproof is done. We're not allowed to use 6 through 9 again. We're done with that. We then look at 1, 2, 3, 4, and 5, and 10, and ask, are there any inferences we can do with those statements? And there is. We can take A in statement 10 and plug it into number 1. Number 1 says, if A, then get B, C. 10 says A. And 11 gets us B and C. Once you have B and C, we have an AND statement. We can take both halves or either half. I'm trying to keep this short, so I'm going to just take the C instead of both the B and the C. And once I've got C out from 11 because of the AND rule, I then have a second contradiction. Because step 5 says not C, step 12 says C. Since I have C both true and false at the same time, I can then infer out the opposite of this initial assumption. And once we've inferred out the opposite of the initial assumption, we've got if either A or B, then C from line 3 because 5 and 12 contradict. And that was what we were trying to prove. Whew. Anybody else tired? Probably not. I'm going to do all the work. Yes. I believe so, yes. I believe this is from 7.3A, 102.
In the textbook, if this is the correct one, it says that the second assumption, step 6, is A and not A. I know there's multiple different ways to do it, but how did you get to not A?
Well, this goes back to there was more than one right way to proceed. So when making that second assumption, I chose not A, frankly, because I like or statements. I think or statements are easy to use. So there was an or in step 4. It was very close to, it was, recently on the mind when I'm making assumption in step 6. So I just made the not A assumption there. But you're right, the textbook does give the other way to, yet another way to do it. I mean, in truth, in step 6, you could use an A in step 6, you could use a B in step 6, and you could have used a not B. Each of those paths would have led you more or less to the same place. You just would have used them with statements 4, 1, and 2 in a slightly different order. So without the book in front of me, I can tell you exactly what would happen in step 6 if I'd assumed A. I would have plugged it into statement 1. If A, then both B and C. I would have gotten B and C. I would have broken the C out of that, and the C in the subproof and the not C in statement 5 would contradict. Then, since I assumed A in step 6, I would have inferred out a not A in step 10. And then in step 11, I would have used the not A with step 4, which is A or B, and I would have gotten B. Then I would have plugged in B into step 2, if B, then A or C, and I would have broken out an A out of A and C, and that would have contradicted the not A I inferred in statement 10. So the book says something very close to that, I assume? Yeah. I mean, again, there are multiple right ways to do this.
I kind of lost track of your explaining it.
Sure.
From 11 to 12, is it just this 12 just because the 7 has to be already? Because it's you said like it's the
Oh, I'm just being lazy.
Okay.
So if you wanted, you could have 12 BC and 13 BB, because that's an and. You're entitled to use both halves of the and. But I've already thought ahead, and plus I'm trying not to put more things up there than I have to. But I've already thought ahead, and I know the contradiction is going to be with statement 5. So the B, I'm entitled to it, but it doesn't do any work for me. Yes, ma'am. You should assume a good chunk of it. You should assume 20 to 30%, something like that. Enough that you'd want to learn the proofs. Now, some people would demand that 100% of the final should be on chapter 7. But because, there's a reason you're shaking your head, and I understand it. Yeah, I don't want to. I know a certain number of people will struggle a lot with this stuff, and and I don't want to destroy you. So I'd much rather have you struggle with 20 to 30% of the exam be proofs and give you some partial credit. There's partial credit opportunities. So even if all you know is start by taking the opposite of the intended conclusion, that you can get a point for that. Now, 1 point out of 5 or 10 points isn't a lot, but it's not a 0. So the more credit I can give you, the better. All right, let's do this one, and we're gonna do this one together. And you collectively are gonna tell me what to do with this one. It's always dangerous to let students tell you what to do and where to go, especially when they're worried about them. But anyway, all right, so premise one and premise two. Premise one, if A then B. Premise two, either A or both A and C. That looks like I need an eraser. Where'd my eraser go? All right. From that, we're going to get both A and B. All right, so what do we do first? Good, assume the opposite of the conclusion, which is not both A and B. All right. Then what do I do next? Well, next I try to use S&I rules. I look at step one, which says if A, then B. So if I had an A or a not B somewhere, I could do an inference with that. I don't have that. I look at statement two, which says either A or both A and C. So if I had a not A or a not both A and C, I could do an inference, but I don't have that anywhere. And I look at statement three, which is not both A and B. So if I had an A or B, I could do an inference. So I'm stuck. So I can't do any S or I rules. So what do I do when I'm stuck? Make another assumption. Very good. All right, so statement four is going to be another assumption. What should I assume? Yes, not A would work. So let's try not A as our nested subproof assumption. So step four is going to be not A. So then I go back to steps 1, 2, and 3 and ask, can I do an inference? And the answer is yes. Not A plugs into step 2, which says either A or both A and C. So since I have a not A, I can get out a both A and C from the or rule from 2 and 4. Now I see I've got an A and a C in the and if I pull that A out, I will contradict the not A. So let me just grab that A real quick. And step 6 will be A from step 5 because of the and rule. Once we've done step 6, then the subproof is over because 6 and 4 contradict. So step 7 will be A from 4 because 4 and 6 contradict. All right, now that we've got 7, now we have to block off 4 through 6. We now cannot use 4 through 6. So we look at 7 and we look back to 1, 2, and 3. And what can I do with A in 1, 2, or 3? Well, the first thing I look at is 1. I've got A in step 7. I've got if A then B in step 1. I can plug that into step 1, and I can get B from 1 and 7, the MP error rule. So I just used 1. I used step 2. I used premise 2 in our subproof. So I bet I should probably use step 3 for this next inference. And it says I can't have both A and B. So I'm going to take that A in step 7, and I'm going to plug it into 3. It says I can't have both A true and B true. Since I've got A true in 7, I can get a not B from step 3. So that's from 3 and 7, the not and rule. And gee, look at that. 8 says B is true. 9 says B is false. That is a contradiction. So step 10, the final step, will be the opposite of our assumption in step 3. It will be that both A and B are true from 3 because 8 and 9 contradict. How's that look to everybody? Make sense? So here's something fun. I did this problem in the PowerPoint, but I did it differently. So here's what it would look like if instead of in step 4 saying not A, assuming not A, and when I did this on my own, step 4 was A. And you can see I I assumed A in step 4. I used it with step 3 with the not and rule, also called conjunctive syllogism, to get not B. Once I've got not B, I use that with step 1, which says if A then B, and not B got me not A from the right to left arrow rule. The opposite of the right gets us the opposite of the left. So we also had not A. And since we had A in step 4, not A in step 6, we had a direct contradiction in our subproof, which allows us to infer the opposite of our nested assumption. So from 4, since 4 and 6 contradicted, we derived not A. Once I had not A, then I used not A with step 2, which says either A or both A and C. So it's an or rule. So we use the not A to contradict the A to infer out the both A and C. Since step 8 is an and, we can break out either half of the and. So I broke out that A. And then we had another contradiction because 7 says not A, 9 says A. Therefore, we could infer the opposite of our initial assumption. The opposite of not both A and B is both A and B. And bam, there we have it. So 2 completely legitimate ways to do the same problem. And frankly, again, there were ways to do this by assuming B and assuming not B as well. Or just as difficult. So what do you think? Should we do another one together? Yeah, we should do it. Why not? Here, let's. All right, let's look at 7.3. All right, one premise. If, not A, if and only if, B from this, we are going to prove it is not the case of A if and only if B. No, it's right. All right, so what do we do? What do we do first? Come on, somebody tell me the magic words. Assume the opposite of the conclusion. Very good. So let's start with assuming if A, if and only if B. That's going to be an assumption. Then we look at these and we start doing S&I rules. Now maybe we haven't used the triple bar rules a lot, so I remember them though. So from 1, we can get if not A, then B, and if B, then not A. Those are from 1 triple bar rule. And then I'll put a little tick mark. Then I look at 2, and I say, well, gee, I can use that same triple bar rule again on 2. And that will get me steps 5 and 6. Gets me if A, then B, and if B, then A. And I'll put a little tick mark next to that to remind me that I've used it. That's 2 triple bar. Whew. But you know what? Then I'm stuck. So what should I do now that I'm stuck? Make another assumption. What should I assume? I should assume B. Why do you want me to assume B? That's right. If I assume a B, here I'll assume B. So I'll do a nested farther in assumption. I'm going to assume B. And with B, 4. So 4 and 7 gets me not A. But then I plug B into 6, which will get me A. From 6 and 7. And once I've done that, I have a contradiction pretty quickly, which gets me the opposite of B. So I'll start up here, 8. I'm sorry, that's not 8, that's 10. Step 10 is going to be the opposite of our assumption in step 7. It will be not B. From 7, because 8 and 9 contradict. Now, once I've got not B, then I need to go back and look at 3, 4, 5, and 6. 3, I have the opposite of the right, so I can get the opposite of the left. So step 11, I'm going to get A from 3 and 10. And then I'm going to look at 5. It says if A, then B. I've got the opposite of B, so I can get the opposite of A. So step 12 will be not A from 5 and 10. Then once I've got that, I have another contradiction. I get to infer the opposite of our initial assumption. So we've proven in step 13 that it must be the case of not if A, if and only if triple bar B. That's from 10. That's from 2 rather, because 11 and 12 contradict. Bam. Now note, in step 7, B was one legitimate thing we could have done, but you could have done B, you could have done not B, you could have done A, you could have done not A. And you would have used statement 3, 4, 5, and 6 with the different arrow rules and different combinations, and you would have ended up at the same place. All right, how are we feeling with this? Show me 2 thumbs if you're, you're excited. I've just handed you over nuclear weapons. Show me wavering if you're not so thrilled, and show me thumbs down if you still have no freaking clue what I'm talking about. I mean, be honest. All right, so that's where we are now. We're at the end of this period. We're going to do 7.4 next time. Work on this a little bit, and we can talk about this a little bit again. Next week. Certainly in the review session, we'll talk about this a little bit. But this is the sort of thing we've been pushing for from day one. I've now given you, a powerful ability. You can do 13-step proofs with this sort of tool. Some people even do this for fun. And you're thinking, get a life, buy an iPad, get a Netflix account, go on a date, do anything but this. Anyhow, take care. See you on Monday. Enjoy the Spring Fest this afternoon. Hey.